My name is Sean DuBois, and before we really get into talking about WebRTC, I want to talk about my perspective of it. I come at it from a very different angle than if you had been building just WebRTC applications in the browser. For me, WebRTC more was a tool to get existing content into the browser. So I started at Lightstream, which is a cloud-native live streaming application. So it's basically OBS for the web. You can bring in sources from multiple computers, you can play a game, or you can co-stream with other people, and that's where I started off in this space. And when I left Lightstream and before I went to Amazon, I worked on a project called Pion, which is a Go implementation of WebRTC in turn, and we'll talk about more of the details. Then at Amazon, I worked on Chromium and KVS WebRTC, which is an embedded implementation of WebRTC that was targeted at security cameras and robotics and drones, and in an area that really hadn't been the focus of WebRTC implementers. And from that knowledge I had learned, I had then started working on a book called WebRTC for the Curious that's completely open source, and it's on GitHub, and you can see it at webrtcforthecurious.com. And now I work at Apple. So WebRTC for the Curious, I wanted to write a book on how WebRTC really works, not just talk about the public APIs. You see the same tutorials on, create offer, create answer, set remote description. I wanted to talk about what's actually going on below that, a deep dive on the protocols. And in that same vein, that book includes an entire chapter on the history of WebRTC and interviews with RFC authors and how they contributed to WebRTC. It's very interesting to see when these protocols were designed, what were the use cases and what did people intend to do with them? It's amazing how WebRTC is used so differently than its original intentions. And then I also wanted to share the WebRTC in practice. So from doing this, being in the space for about 6-7 years now, you've learned a lot of debugging tips and little things like that, and I wanted to share that so that when people are building their WebRTC applications, they can know about the sharp edges before they hit them. And the project that informed WebRTC for the Curious was building Pion, which is a collection of Go RTC libraries. And instead of building a monolithic server, I wanted to do building blocks that were designed to be flexible. The first project was the peer connection API in pure Go, which is what you use in the browser. So in Go, you can call webrtc.createOffer and create a peer connection and connect to the browser or connect to an iPhone or anywhere else. And it is a pure clean room implementation of WebRTC. It doesn't use any other libraries. It's all in Go. And anything we had to do, we had to write ourselves. And so people use it to do servers, people use it to do teleoperation, cloud gaming, lots of interesting things. Pion also has a turn server and client, which was designed, again, I didn't want to have more monolithic servers. I wanted to have something where you had callbacks for authentication. You could bring your own logger. You could embed turn into your existing application. And then Ion, which is a cluster-based system for building RTC. And the idea is that you can spin up instances for what the application you're trying to build. So let's say you're trying to build a conferencing system. You could spin up a bunch of SFUs. Let's say you're trying to build in some kind of AI-powered thing. You could spin up an AVP instance, which allows you to process real-time media coming from the browser via WebRTC. So what is WebRTC? It's kind of an overloaded term. People will say, oh, that's built with WebRTC. That uses a little bit of WebRTC. That's not actually WebRTC. What's the actual definition here? So WebRTC, it's an overloaded term, and it's both an API and a protocol. So the first part is the API, which is defined by the W3C, which is the JavaScript API that you find in the browser. That's it. But the real meat behind it is the protocol, which is defined by the IETF. And that protocol has multiple implementations. You can use it in C, you can use it in Python, you can use it in Go and TypeScript. There's a company that has an Erlang implementation. There's a company that has a Java implementation. And these are all separate clean room implementations. These aren't just calling one library called, the WebRTC library. These are all separate implementations of this protocol dictated by the IETF. It's a very healthy protocol that everyone can talk to each other and exchange things. So what does this protocol actually do? The protocol allows you to first exchange multiple audio and video tracks, and you can add and remove them at any time. So I can be sending my webcam, and then I can decide 3 minutes later, oh, I'm going to send you my desktop also. And I didn't have to declare that at the beginning of the call. And I can also remove, and there's no restriction on how many audio and video tracks You can bundle them. You can have your audio and video synced for your desktop, but then your webcam runs on a completely different timer. It's super powerful that way. And also you have binary data, and the binary data is made up in datagrams. So you send 3,000 bytes, and those 3,000 bytes are guaranteed to arrive on the other side, and they're packaged as a datagram, no matter what kind of network it's running across. But you can also apply different attributes to those messages you send. They could be lossy, they could be unordered. You can have multiple distinct streams with their own data channels. And that's really powerful when you're building these like RTC applications. You want to do metadata, or you want to build something that's not even in the audio and video space. And then also security is mandatory for WebRTC. It's not an if statement here. Like if you're using WebRTC, it is end-to-end secure. You can do things in the applications on either side. That's a bad decision, but the protocol itself dictates that it must be secured by DTLS. So then WebRTC, then where it gets interesting is it allows the user land to make a lot of decisions. So you can do UDP or TCP between two WebRTC instances. You can choose the route. So between two hosts, there's actually multiple ways I can talk to each other. If you have two laptops in the same room on the same network, they could connect directly to each other, or they could go out to the public internet and come back in, and they could do something like that. And it's not effective, but that's the power that WebRTC gives you. You can choose those routes, and you can also switch those routes at any time. You can do an ICE restart, and I can switch between talking to each other via Wi-Fi, and I can switch to cellular. That's really interesting for roaming and robotics use cases. And that flexibility allows you to build any kind of topologies you want. So you can do a peer-to-peer setup, or you can do a client-server setup where you have a WebRTC connection up to a WebRTC server. You can choose that. And also you get a lot of control over the congestion control. You can choose, do you prefer latency or loss? You can choose who chooses the bitrate. Let's say we're exchanging video. You can have the receiver declare what bitrate it wants, or you can have the receiver send metadata back and then the sender chooses the bitrate. WebRTC is all about like giving you that flexibility to build your application. And where that flexibility comes from is WebRTC itself is not actually, there's not actually a new technology there. It's all just a bundling up of existing protocols. So don't worry about memorizing these numbers. We're going to go through all these RFCs. But the big ones is like, for example, all of the connectivity establishment was already specified. All of the media exchange was already specified. And to break down the WebRTC protocol, I like to think about it in 4 steps. Signaling, which is establishing like who you're going to talk to and what you're going to talk about. And then once you're established, it's connecting. So I know who I want to talk to, but how do I talk to them? And then after you're able to exchange data, then you secure, and then you actually start sending things. So the first is signaling, which is just exchanging the minimum amount of details to start the call. You have this kind of global state, which is your authentication and your candidates. And then you have things like your DTLS role and your fingerprint. And then you have your media sections, which is like, these are the codecs I can receive. These are the tracks I want to send to you. The protocol makes no restrictions around codecs. That's kind of a misnomer you hear from people. The codec restrictions are from the agents. So if your browser decides it doesn't want to implement H.264, that's something that's common, and there's a lot of politics and other conversations around that. But the idea is that in the session description protocol, you say the codec you want. And if both agents support that codec, you can exchange. So this is what that bootstrapping looks like, is that you exchange a bundle of key value pairs, and those key value pairs tell you what you're going to talk about. So at the top level, you have your global details. And then after that, you have a media section. And what that media section does is it says, okay, I'm going to send you my audio, and these are the codecs I'm willing to support, and that's it. And then next, you have your video, and this is what I'm going to send you, and these are the codecs I support, and that's it. So now we're ready to talk. I know, like, okay, I'm going to talk to someone. They're going to send me one audio track. They're going to send me one video track. These are the codecs it's going to be, and these are the places they're reachable at. So now it's time to connect. You have 2 roles, controlling and controlled. One side makes the choice about these are the this is the IP address that I'm going to talk on, and the other side, this is the IP address they're going to talk on. And then both sides have auths. And both sides have candidates. And what a candidate is that this is how I'm reachable. So you have a host candidate, which is, okay, this is my local IP address. This is my server reflexive candidate, which is my NAT mapping. And what that is that your router will establish a temporary hole that maps back to your computer. And then you have relay, which is you can actually run like a proxy on a public host, and you can route all your traffic through it. So once you have all these pairs up, you have what you call candidate pairs. You have your controlling agent with its pairs, and you have its controlled agent, and then you bundle those up and run checks, and you figure out like what's the best way to talk to each other. But what is the best way? Like, do you want the candidate pair that connects first? Do you wait for the best pair? What is the best pair? Is it with the fastest round trip time, with the least packet loss, with the least bandwidth costs? These are all things that the application gets to decide. And WebRTC also lets you stay connected on the move. So you can announce candidates to the other side as you move, and you can nominate new candidate pairs by doing an ICE restart. So next is securing. And what the WebRTC does is it does a DTLS handshake. And the DTLS handshake, it really is just a minor extension of TLS just over UDP. And once you do that TLS handshake, you can then extract the keying material and then use it to encrypt your video packets. So the one interesting point about WebRTC is it doesn't use a central authority for trust. When you do a handshake with a WebRTC agent in the SDP, that's where it says, okay, this is my certificate. And when we connect peer-to-peer or directly, like I should also be using the certificate. So this is how it makes sure that the person you did that bootstrapping message with is actually the person you're talking to. And that's where the trust comes in. There's no reason that you can't bake in your own certificates, but this is how it's done in the browser where you don't control who generates the certificate. And next is media communication. So we've connected via ICE, we've secured via DTLS. Now it's time to exchange some video. And video in WebRTC all comes down to constraints and solutions. So we have constraints like this is the bandwidth, this is the hardware, this is the network. Maybe the network is really lossy, maybe it has jitter. And what are the certain knobs we can tweak to give people a better experience? You can do the keyframe interval, the coding complexity, the bitrate. And you say basic, but here's a graph out of Chromium that shows like this is what the call looks like. You have packets lost, you have the total decode time, all these other things that you have to pay attention to and try to figure out. And the video in WebRTC, it's all exchanged via RTP, which is a protocol that was standardized in the early 90s. And all it comes down to is like, how do I chop up a large video frame into a small little UDP packet? And then how do I make streams out of them? An RTP packet just adds a little bit of header on top of the video frame with some certain things like this is the unique ID of this video frame, this is the codec, and this is the timestamp. And then when you deal with RTP, like these are the common problems you have: delay and reorder, latency, and then you have some interesting solutions to those. So WebRTC gives you a couple. You have NACs. So let's say I send you 3 packets and the middle one is missing. What you can do is you can re-request that middle one because the sender doesn't know what was lost. It's up to the receiver. And then you have PLIs, which is where you can request that you restart the entire encoding session over. You've gotten it into an unrecoverable state. And you have FEC, which is when you send the video, do a little bit of duplication because if I lose something, it's not a problem. So here's some visualizations. The first is packet loss. So the red packet is one that's been lost. How do you decode something where you're missing like one little part? That's where the NAT comes into play. And the other one is jitter. So if you look at those packets, you have 1, 2, 3, 5, 4, 6. You have packets out of order. So RTP helps us arrange them back in order. And again, RTP is all about trade-offs. Do you care more about latency? Do you care more about quality? Does one track matter more? When you do like the error concealment algorithms, like which is the best one to do? And then you have congestion control. So you have two choices. You can do receiver-driven congestion control, which is the person that is receiving the video sends just a single number back and says, please send me video of bitrate, 3,500. And it's up to, and the sender has to respect that. Or you could do sender-driven congestion control, where the receiver sends the reception status back, and then the sender chooses the bitrate. This is cool because the sender is aware of jitter, packet loss, and much more. And it gives you a chance to play with the algorithms. So this is good if you're running a WebRTC server and you want the server to not be very smart. All the server does is it sends back these reception reports, and the sender does a lot more. And this stuff is still ongoing. There is a IETF working group that's still discussing what is the best algorithm to do for congestion control. They have all these great graphs and show this is suggestions for different workflows. And then the last one is the data communication, which is the SCTP protocol. And what you've got there is you've got multiple streams. Each of those streams have distinct behaviors on should these packets stay in order that I send? How often should I try to send them? And the SCTP protocol is really simple. It's all about chunks. So inside a chunk, you have a data chunk, and that data chunk just contains a little bit of what you sent. You have the global transmission sequence number, which is this is packet 3000 of the total of 3000 I've sent. Then you have a stream identifier, which is, this is stream A, and then you have the number inside the stream. So this is packet, 5 inside stream A. And then when I receive a packet, I send back a SAC, which is selective acknowledgement. And that just says what's the last packet I saw? And it does some really cool things. So let's say you want to send a video frame to a remote host. But if that video frame is broken, you don't want to send the whole thing. Other protocols, they send the whole thing, and that's all you can do. But what SCTP will do is if it detects that it lost a single packet out of the entire thing, it won't try to send more than it needs to. So if you're sending 1,000 packets and you lost packet 3, it'll just skip to 1,000. SCTP has a lot of interesting optimizations like that. So here are kind of the unique problems that WebRTC can solve for you. The first is ICE and how it helps you connect in interesting situations let's say you don't have any direct connectivity. NAT Traversal is a solution. So what we talked about earlier with server reflexive peers is that my local WebRTC agent will send up to a server, and that server will respond, and that will establish a temporary NAT mapping in my public network. And what that gives me is that what people like to call their public IP now has a temporary port that maps to your local machine. It's almost think automatic port mapping. Instead of going in and saying port 5000 maps to this IP address, it's port 5000 is automatically mapped for a limited amount of time. And all that you had to do was send a packet to a stun server, and it creates that mapping. And that's how a lot of WebRTC connections are made, because you have this NAT traversal. The next is what happens when one call leg goes down. So let's say you're on the phone with someone and you're talking to them via your Wi-Fi, but then your Wi-Fi goes down. You can do an ICE restart and start flowing over the other side. And then congestion control. So you already have, if you've used HLS, you're familiar with this, but it's not enough to just measure the quality of the connection at the start of the call. When you start that call, you might be the only one using your Wi-Fi. But then what if 3 more people come online? All of a sudden, your Wi-Fi doesn't have as much bandwidth available as it did before. And other things like you can have more packet loss and things like that. And so the congestion control is the receiver will send back and say I got these many packets, I lost these many packets, I have this much delay, and all those things like that, so that you can have a better experience. And here's a more interesting one that's kind of new in the WebRTC world, which is the MDNS. So you can put 2 hosts in the same network, and they don't even need to know each other's IP address. What they use is something called multicast DNS. And you basically send an announcement out to your network and say hello, I'm laptop B, and this is my IP address. So you can have two peers connect without knowing their IP addresses ahead of time, without having to worry about like bootstrapping that detail. And that's going to open up a lot of like interesting zero conf situations. So if you've used protocols where you can like cast your laptop to your TV, like we're going to get to a point we're going to be able to do stuff like that with WebRTC, where you can connect two WebRTC agents in the same network without having to worry about pre-existing configuration. And then the big problem that's solved by SATP is the head of line blocking. So if you sent something that's really slow in the past, we don't want to keep blocking on that. So like telemetry or metadata, you don't care about the subtitles from 5 seconds ago. So SATP gets around that by it only sends new data. It doesn't worry about retransmitting old stuff, which is very powerful over TCP. And then these are some projects that are built using Pion that I think are interesting and wouldn't be possible using other technologies. So Nintendo Switch Remote, a developer put an HDMI output to WebRTC on their Nintendo Switch, and they're able to send that video into their Oculus. So using WebRTC sitting in the same network, I can sit and have my Nintendo Switch in my hand, but all the video frames go to a VR headset that I'm wearing. So it's kind of bringing those like game streaming use cases, but even inside your own LAN. You don't have to worry about having cables connected and other stuff like that. And it keeps the headset dumb. You can have a cheap headset, but a great gaming PC. Cloud Retro is the ability to play a NES game in the cloud. And when you play this game, you can also play it with others. So me and you can both open up this user interface and we can play together. I can be player A, you can be player 2, and we can play together like we're sitting. It was a really unique experience playing this for the first time because it really captured that spirit of sitting on the couch and playing a video game with someone else, especially during like this whole COVID time where you couldn't be in the same room. I've been playing this a lot with people. We just open up a video call and play a game together, and it's a lot of fun. This is Nico, and the idea is you can host a web browser remotely, and then you can share it with a friend. So you could watch a video with someone else. Something I've been playing with lately is you can record a conference with someone else. So let's say you can actually join a Zoom call using Nico, and you can record like it's a web browser that's running locally. A lot of people they want to script web browsers and stuff like that, and it's an interesting thing to play with. And here's the teleoperation cases. So a telodrone, you can now control it in your browser by just dropping these little operations, and it'll send them over data channels to the drone. And now it's able to fly around, and you're getting the video feed out of it. And the flexibility of WebRTC lets you do that. And then WebRTC isn't just like a browser technology. Here's a use case where a terminal application written in Go is communicating with a browser. So you have a browser and a binary application that are sending video over the internet. And because WebRTC is the standardized technology that allows people to talk, you have that kind of interoperability. Strive CDN was an early adopter of Pion that I found really compelling, where imagine if you have 5 people inside the same LAN, they shouldn't have to download the same one video 5 times from a remote host. In this case, one user downloads the video and then it exchanged with everyone else. And then with Pion, another person was able to bring life to an existing RTSP camera. So before, with an RTSP camera, you can only view it with like a dedicated player that's a native application. By using Pion, they were able to do an RTSP to WebRTC bridge right on the device. So now they can just connect to the device and watch their security camera. And then also bringing that NAT Traversal to other applications. So a lot of people, they'll have jump boxes to get in their networks. You'll SSH into the public host, and then you'll go to ones behind the network. By using something like this, you don't have to do that anymore. You can, using NAT Traversal, just connect directly to each other and not have to worry about putting your hosts on the public internet. You just open up a temporarily NAT mapping so you can talk to each other. And RTC Tunnel is a project that does the same thing except for TCP services. So the idea is that in your browser, you can connect to a WebRTC host via data channels, and you can access TCP services. So you can access Redis, You can access SSH. It allows you to get into everything at the protocol level, which I think is very, very interesting compared to doing like a remote desktop or something like that. Snowflake was another project that was really exciting to work with. If you're using Tor, you have to download a binary to access the network. Snowflake makes it possible to access Tor just via data channels. And it's a protocol that's really hard to block because it's being used for all of these business use cases. And you don't have to download anything because it's already in the browser. And then Web Wormhole is another one where you have these existing file exchanges, but it's like it's written in Python only or something like that. Web Wormhole, because it was written in Go, you can run it on your desktops, you can run it on your phone, and then you can use the web UI via WebRTC and exchange files. So now you're able to exchange files between any platform and the web. And then here's a visualization of the Ion project we were talking about earlier, which is bringing like a modularized way that you can build your own RTC systems. So thank you very much and hopefully you learned a little bit about WebRTC. I encourage you to reach out to the Pion project. We have a Slack channel, we have active Twitter, and we're just trying to make this technology easier to use. WebRTC is a super powerful technology, and it's standardized, and it works well. I think it's perceived as difficult, and it's just an education issue. So my hope is that through things like Pion and WebRTC for the curious, we're going to enable people to build more interesting things with it.